So one of the things that we will have to adjust to is the fact that there is not a periodic table provided on the Pcat. And so I'm going to put in some periodic table details. And really what I want us to focus on are some trends, and then just to look at a few couple examples of how we can use the rich amount of information contained in a periodic table in order for us to answer questions. So in group 1, we're going to have the alkali metals, and even though hydrogen is not a metal, because of its electron configuration, it's placed in group 1. So everything in group 1 has one valence electron. We have hydrogen, we have lithium, we have sodium, we have potassium, we have rubidium, and we have cesium. If you're really feeling squirrely, you also have francium. In group 2, we have beryllium, and we have magnesium, and we have calcium, and we have strontium, and we have barium. By the way, barium is a very special element. It's one of 2 elements that are called the medical elements. The other one is Cu, or curium. And the reason they're called the medical elements is that in medicine, if you can't cure them, you bury them. Little humor, little humor. All right, so let's skip all the way over to group 13. So we're going to have boron and aluminum and gallium and indium. Then, of course, going across the row, we have carbon and nitrogen and oxygen and fluorine and neon. And silicon, phosphorus, sulfur, chlorine, and argon. Germanium, and let's think for a second. Selenium, tellurium, bromine, iodine, krypton, xenon, I think I'm going to stop there. That's probably enough for us to get by with just about any question that we would be asked. By the way, if we start numbering the elements in terms of atomic numbers, of course, let's not forget about helium, which is element number 2. So you notice we've already placed the first 20 elements on the periodic table. And I think it's fair to say this represents probably more than what you'll need to know. But a little extra knowledge isn't going to kill us. And these atomic numbers are just for reference. So let's envision a couple of questions that we could answer given a periodic table. So how many valence electrons would we expect phosphorus to have? So what I'm going to suggest to you is that when you find phosphorus on the periodic table, which is element 15, the first thing that you should do is completely ignore the energy levels leading up the period to the period where phosphorus is. So it's a third row element. Let's only consider third row electron configurations. We have a 3s2, here they are, sodium and magnesium. That of course is 3s. And then in 3p you have 3 orientations because there are 6 elements. But I only need 1, 2, 3 to get to phosphorus. Hund's rule says I need to place 1 electron in each orientation. I have 5 valence electrons for phosphorus. If I don't consider the process of hybridization, I can make 3 bonds as indicated by the 3 lone electrons, 1, 2, 3, and I have 1 lone pair. However, we have 3d unfilled orbitals in the third row of the periodic table, which means I could also promote or hybridize one of these from the 3s. This of course requires energy to do so, but notice the payback that we're going to get. We go from being able to make 3 bonds now to being able to make 5 bonds. Those 2 more bonds will be more exothermic and they will release the energy that more than makes up for the initial energy input required for hybridization to occur. Not only that, but hybridization also means how we mix the orbitals. And orbital mixing makes bonds stronger. So there's a 2-pronged payoff in hybridization. Let's take the time to review that. So hybridization, which is a man-made invented process to explain how bonds are made in nature. This was invented, of course, by the father of bonding, Linus Pauling, who was at Caltech for a number of years. Pretty smart fella. He obtained his PhD when he was all of 22 years old. Graduated college when he was all of 16 years old. I think it's safe to say he did not have much of a social life with the ladies. So hybridization includes 2 processes. One is electron promotion. By the way, this is an endothermic process. And number 2, orbital mixing. From this, I make more bonds. That's a payoff. And I make stronger bonds. This idea that I can represent the electronic structure of an atom with arrows and orbital diagrams, I call this Odec, which stands for Orbital Diagram Electron Configuration. You can use this to answer a number of questions. For example, the formal charge of an atom in the context of a molecule. Let's say we have a carbon-carbon double bond, a carbon-oxygen single bond, oxygen-hydrogen single bond. We have a carbon-hydrogen single bond. We have a lone pair on a carbon. We have a positive charge on another carbon. What is the formal charge on this carbon? Well, this carbon is making 1, 2, 3 bonds. It has one lone pair. We know carbon is a second row element. If it's making 3 bonds, I have to have 3 lone electrons, and if I have a lone pair, I must have another that is paired up. Here's my 2s, here's my 2p. To find the formal charge, I need the number of valence electrons of carbon, which of course is 4, and I subtract the number of arrows from Odec, which is 5. 4 minus 5 is -1. This carbon is better known as a carbanion, and it has a negative charge. A lot easier to do it that way than memorizing a bunch of rules or using the method that everyone is exposed to, S equals M minus A. Lewis structures work more easily this way. Finding formal charges work more easily this way. Finding geometries works more easily this way. Finding the exceptions like radicals or things that don't have an octet or things that expand an octet are easier to visualize when you use the Odec methodology. And that's just one example of a particular problem. So let's look at a couple of periodic table quantum questions that you could see on the Pcat. So I'd like to start with this question. We have an element that has an electron configuration as follows. It is 1s2, 2s2, 2p6, 3s2. When this element becomes an ion, what will be the charge? Answer choice A is -2. Answer choice B is +2. Answer choice C is -6. Answer choice D is +6. This is a question you must get right if you want to go to pharmacy school. So let's talk about how we make this simple. The driving force for making ions is to have a completely filled s orbital and a completely filled p orbital. We call that the octet rule. This molecule can be given an octet if it does one of two things. Number one, it could lose the 2 3s electrons. Let's see what would happen if that occurred. We could lose the 2 3s2 electrons. This would give us a full 2s and 2p. Notice the full 2s and 2p adds up to 8 electrons. That's why it's called an octet. If I lose 2 3s electrons, that would have a charge of +2. Notice that +2 is one of the answers. The second thing that could occur to get a full octet is I could gain 6 electrons. Gain 6 3p electrons. This would result in a full 3s and 3p, which would give me a charge of -6, which is also an answer choice. So right from jump, -2 is not a reasonable answer choice, and +6 is not a reasonable answer choice. There are two ways we could think about this. We could be very simplistic and say, well, which is easier, to lose 2 or gain 6? And hopefully most of y'all would say to lose 2, which would be the right answer. Or you could use some chemical logic and realize that every time you add an electron, there is a repulsive energy that is going to be introduced to the system. The chances of us squeezing 6 electrons and having it be stable is not very good. I mean, how many -6 ions did you learn in Gen Chem 1 and Gen Chem 2? Answer 0. That's because they're not very stable. So either of those two lines of logic lead us to B as the credited answer for this particular problem. So let's consider this problem again through a different pair of eyes. So I have an electron configuration of 1s2, 2s2, 2p6, 3s2. Choice A is -2. Choice B is +2. Choice C is -6. Choice D is +6. Remember, our overriding principle is we must have in the highest energy level a completely filled S and a completely filled P. So if we look at A, -2, that means we're going to gain 2 more electrons. If we gain 2 more electrons, then I will have 1s2, 2s2, 2p6, 3s2, 3p2. That is not a full octet with the highest energy level. I can eliminate A. If, on the other hand, I have a +2 charge, that means I've lost 2 electrons. Remember, the protons stay associated with the atom. If we change the number of protons, we change the atom. So the only way we get plus and minus charges is by removing or adding electrons. If the charge is negative, we've obviously added electrons. If the charge is positive, then obviously we've removed electrons. If I remove 2 electrons, now I have 1s2, 2s2, 2p6. That is an octet. We should keep answer B. Let's look at C. I would have to add 6 electrons. 1s2, 2s2, 2p6, 3s2, 3p6. I want to keep that answer as well. Finally, I can take away 6 electrons. I would have 1s2, I would have 2s2, I would have 2p4. That is not a full octet. I want to eliminate D. So I have to either pick B or C. Now, there are lots of ways of attacking this, but let me kind of go back and give you a non-chemical analogy that will hopefully make sense. Let's imagine that having these energy levels is analogous to having hotel rooms, and we are the owner of a hotel, and our hotel is not filled. If I were to have this electron configuration, it would be analogous to allowing other rooms in the hotel to open, but we're not bringing in any more money. We'll have more overhead because more rooms are open. It's more financially feasible for us to have less rooms open, taking in the same amount of money, but having an electric bill that's not as expensive. B is the best answer because energetically, losing 2 electrons is more feasible than gaining 6 electrons. Secondly, and more importantly, look at what element this represents. This represents magnesium, element 12. Magnesium, IUM ending, always denotes a positive charge. It cannot be a negative charge, meaning C should be eliminated and A should be eliminated. And a +6 doesn't result in a noble gas. D should be eliminated. We still come to B as our answer. So there's a lot of different ways you can attack this problem, but we have to come to the conclusion that B is the best answer.